Now, what we're interested in is exploring the risk in this. What are the things that could go wrong, and where are the possibilities for extending this and making a mockery of our assertion to say that we could do it in this time period of 48? Well, for that, we come up with a new concept, and that's the latest start times and the latest finish times. And back to my little box here with the descriptions on there, we use late start, LS for late start, and LF for late finish. And these are used in a very, very simple equation to say, well, how do we find out what the late finish is, or the late start? And we have a simple equation that goes like this, that the late start is equal to the late finish minus the duration. I'm going to call that equation 2. A demonstration of that will make that much more clear. This is a closed system, as we'll know. There's one activity at the start of the network and one activity at the finish. And one of the properties of this last activity here is the late finish is also equal to the early finish. So this late finish of the last activity is 48. So we've got a registration point here, and it means that from there we can calculate what that late start was for that activity. Simply using that equation 2, we take the late finish and subtract the duration of 9, and that gives us this answer back here, 39. Very simple so far. We can move that backwards through the network, because what we're doing now is a backward pass. And we can say that the latest finish time for activity G is the same as that late start time for activity J. That'll be 39. Remember, we're talking time units, not days, not weeks. This is an abstract here for you to understand the logic and the timing and the equations. So that 39 operates in activity H, and it also operates in activity F. We look at activity G and say, well, what's the latest time we can start G without affecting the end date of the project? And that's a key assumption. We're now looking at the latest start and latest finishes of these activities to do that without affecting the end time of the project. That's where we're at. So we can subtract the duration from 39, which is 39 minus 11, giving us 28. On H, we'd have 39 minus 12, which gives us 27. And on F, we'd have 39 minus 7, which will give us 32. So we have the late starts for activities F, G, and H in this backward pass. And we can proceed through this network, eventually finding out all the late start times and the late finish times. So I'll move backwards onto E, and that's the late finish is determined by the late start of H, which is 27. Gives us 27 there. We can calculate the late start of E by subtracting the duration of 12 from the 27, and that gives us 15. We're in a position then where we can move back to some various other possibilities here. And in this particular case, we can simply say, well, it's quite a simple network, this one. We'll add some complexities later when we're varying this, but B, the latest finish time for B is the latest start time for E, which is 15. And for the latest finish time for C is actually late start time for F, which is 32. And 15 is the late start time for E. It's also the late finish time for D. And we can use the other attributes of B and C and D to work out their late starts. So the late start for B is the late finish of 15 minus the duration of 10, which will give us 5. The late start for C is the late finish of 32 minus 7, which will give us 25 as the late start. And the late start for D is 15, its late finish, minus 8, which will give us 7. So we've nearly populated the whole of this sequence of activities in the network with the late starts and the late finishes, and we're just left to do activity A. Now This could have happened at any stage in the network where we had a complex of more than two successors or two or more successors to an activity. It didn't happen down there because the job wasn't that complex. But here we've got three activities that are held back or restrained by activity A. So the late finish of activity A is determined by three succeeding activities. So we have a choice there of 5 for B, 25 for C, and 7 for D as being the late finishes for activity A. What is the latest time activity A can finish without affecting the end date of the project? And when we did the forward pass, we had to choose between two of these. We took the maximum. And we can reason ourselves through why we should operate with a choice in this situation. And we could do it simply. We could say we were moving forwards and we took the maximum. So now when we're moving backwards and subtracting the durations, it's probably the opposite of that. So it'll be take the minimum going backwards. We'll park that as a very good estimate of being the right answer. And let's examine it with a bit of reason. If the late finish for A could be, let's say, 7 instead of the postulated 5, it would mean that that late start could happen and we would not affect the end date. But if this could finish at the late finish of 7, this would have a late start of 7. Then it would have a late finish of 17. This would have a late finish of 17, driven by that activity alone. And it would be 17 or 15 as being the choice there. So this would be 17, the maximum going through there, plus 12 make this 29, and so on. And you can follow my reasoning. And we would probably end up with an increase in this early finish time of approximately 2 time units, and that would come to be 50. So 7 cannot be right. What we've done is a proof by induction there, shown that this can't be true. I won't bore you by doing the 25, but you could do that exercise yourself. So I'm going to suggest that this late finish is 5. To get the late start for A, it's 5, the late finish, minus the duration, which is going to give us 0, and that's happily the right answer. Why is it the right answer? Well, because this is a closed system. And the late start and the early start for the first activity will be the same. If you get a different answer there, your arithmetic going through these equations has been incorrect.